Alright, this is still chapter 3. We're ready to start part 2 of section 1, which talks about forces. Well, the whole section is about forces, but we're ready to start talking about weight. So, here we go. Alright, so first of all, we are going to talk about some forces here. We have 4 basic forces. We have electromagnetic force, and some of these forces that we have in physics, these are kind of the 4 basic forces we have in physics. First, we have electromagnetic force, and we'll talk about this one later, probably second 9 weeks when we talk about electricity and magnetism. So this one's kind of a little later. These we'll probably hit a little bit even harder in most likely chemistry, when we talk about the whole idea of nuclear chemistry. That's the biggest thing we hit it with, like fission versus fusion, some of those. These are more when you're talking about atoms and things. They're a little bit more common, which of course you still get into with physics, but we're not going to hit those in this semester. That'll be second semester. But the one that we're going to hit big time this semester, one of the 4 basic forces, is gravity. And so gravity is the attractive force between any 2 objects that depends on the masses and the distances between them. So as long as you know the mass of the object and you know the distance between those objects, you can figure out what the gravity is. And so our famous scientist, our favorite scientist, shall I say, Sir Isaac Newton, formulated the law of universal gravitation. Basically the law of gravity, if you want to call it. And he didn't formulate this nice little law by sitting under an apple tree and an apple fall on his head. That just didn't happen. He did, however, do a lot of complicated, that's a hard word today, complicated calculus problems. And this was back in 1647, so you have to appreciate this. This is back like before, you know, modern plumbing. This is like the earlyhood of even chemistry, before chemistry was even born. So we didn't have a periodic table, most likely, things like that. So you got to appreciate that. And he came up with this nice formula. Now, this is going to be an appreciation formula, meaning I'm not going to expect for you to memorize it. I'm not going to expect for you to use it. It's just going to be one of these that this is how they actually calculate gravity, where they take the mass of the first thing they're talking about, like for example planets. They take the mass of the first planet, they take the mass of the second planet, they take the distances between those 2 planets, and they square them. And then we have a universal gravitation constant that is, there's a whole long way to figure that out, and that's how you get the force of gravity. Now, the things you do need to know about the law of universal gravitation is that the force of gravity can be calculated between 2 objects as long as you know the masses and the distances. So that's the key. You've got to know how much that object weighs, and you've got to know how far they are between each other. The other thing that you need to know is that if you take the masses, if 2 masses decrease, then that law of universal gravitation is going to increase. So those are just some things that you need to know. Okay. Now, something else about gravity is that no matter how far 2 objects are from one another, gravity never completely goes to 0. You can get it down to where it's like, 0.000, but there's always going to be some gravity. And they call that a long-range force. Okay? So it's one of the long-range forces, which means that it never completely disappears. It's always there. It's going to be, there's always some gravity. And we're going to talk more about weightlessness later, because I know probably some of you have this thing in your head where you're like, well, if we go out of space, there's no gravity at all. Well, keep that in mind, okay? For later. go with what the notes say now, and I'm sure I'll answer that question later. Alright, gravity actually exists in a field. We call it a field where, you have this basically this region, and then every point basically has gravity. We call that a field. It's just easier to think about it that way. And so everywhere that Earth's gravity basically lies, where that gravitational field exists, here on Earth, it has a force of 9.8 newtons per kilogram. It will go down, obviously, because we are moving away. So it'll go down the farther you get away from Earth. Now, alright, so we're going to talk about weight. And weight is different from mass. First of all, we need to explain that. When you go to the doctor, they actually take your mass. It's so many pounds, or in some countries even so many kilos. But when you are talking about weight, it's actually a gravitational force. The true term weight is a force, not like pounds or kilos or any kind of, like what you typically think of a weight measurement. So be careful about that. Weight is how much basically force is exerted on an object. And on Earth, it's equal to the force of Earth's gravity. So, and we have an equation for weight. Of course, it's physics. You have to have an equation. So, to figure out weight, it's the mass of an object times the gravitational strength of the object. Now, I'm not a real big fan of this, so I'm going to mark this out. So don't look at this. Use W. We're going to use W equals mg for the equation. So W equals mg is your shortened equation for calculating weight. Notice here, the units for weight. A little, wink, nod, nudge, nudge to the good old Sir Isaac Newton. Mass, as always, we use kilograms. Gravitational strength is newtons per kilogram. If we're here on Earth, guess what you'll be using? 9.8. If you're somewhere else, they're going to have to give it to you. You're going to have to be able to look it up in a chart, or you're going to have to solve for it. So just make sure, and of course this is Earth. So just make sure that you are aware, are we talking on Earth? Most of the time, my homework, I will obviously put it on Earth unless you're solving for, gravity. Because if you're solving, it's kind of stupid to put something else. But anyway, alright, weight examples. Okay, so where our equation is W equals mg, and we said we're going to have W, we're going to have m, we're going to have g, and we already said that weight is going to be in newtons. I'll put that in parentheses. M is going to be in kilograms. And look, right up here in the problems, I haven't even read it yet, but this word is sticking out to me. Earth, hello. So as soon as they say Earth, 9.8 meters per second squared. That's how I label it, and that's what a lot of people use, is meters per second squared. It's the same thing as a Newton kilogram. So, here we go. So let's see, calculate the weight of an object on Earth that has a mass of 50 kilograms. So 50 kilograms, mass is 50. So we're going to calculate the weight, that's unknown. So this is going to be one of those straight multiplication problems. M is 50, G is 9.8. So 50, 9.8. I take my handy dandy calculator. 50 times 9.8, and I get 490, unless I did something incorrect, which doesn't look right, or I mean does not look wrong. 490. You're solving for W, which is going to be labeled newtons. So the force or the weight of that object is 490 newtons. Okay, let's try another one. Alright, so I know my formula because these are all weight examples per the title. W equals mg, W, m, g. Alright, calculate the mass of an object on Earth. Again, it says Earth, so I can go right down here, 9.8 meters per second squared. that has the weight of 775 newtons. So they're giving us the weight. And if you didn't know it was weight, look, it's labeled newtons. So the weight is 775 newtons. So look, the only thing you do not have is the mass. So guess what? Plug and chug. W is 775. Mass is unknown. I'm going to leave that as an M. My G is 9.8. So look, you're going to have to divide each side by 9.8. So 9.8s are gone, leaving you M, but you still have this over here, which means you're going to have to take your handy dandy calculator, divide 775 divided by 9.8. And so that's the same thing as 79, and it goes on 0.0816, so maybe like 79.1 kilograms, because it's mass, so you would label it kilograms. And there's your answer. So just kind of compare, and this is to show you that your mass would be this on Earth, but then you could compare it and say, okay, well, this is your mass on Earth with this weight on Earth, but then with this mass, what would your weight be on, I don't know, Saturn? You know, it should be different because their gravity is different. Okay, last one. Bob is going to use this equation. Bob has a mass of 45 kilograms and his weight on Jupiter is 600 newtons. What is the gravity on Jupiter? So here's an example of where you're not going to use the 9.8 because they're saying he has a mass of this, 45, so your M is 45. He has a weight of 600 newtons, so your weight is 600. So look, you have everything but the gravity, so if you put in 9.8 it wouldn't make sense because what letter would you solve for? Plus, look, what planet are we on? Jupiter. Okay? So you need to make sure that you're watching that. It doesn't say Earth. And like I said, on my homeworks, most of the time, I don't put, what planet, but, I mean, if I don't put the planet, it's Earth, unless you're calculating for, gee, I guess I should be better about what planet you're on, but 600 equals M, which is 45, G. Divided by 45, divided by 45. So look, same thing as the last one. So if you're solving for either one of these variables over here, you're going to divide. So all I have to do is take my calculator, take 600 divided by 45. I get 13.3 repeating. And this is going to be meters per second squared, because gravity is actually an acceleration, how fast something's going. So label it as meters per second squared. I would not mark it wrong if you labeled it Newton kilograms, but usually we label it meters per second squared. Okay, so we caught that, right? If you're solving for those two, on that side you divide. If you're solving for W, then you multiply. Okay, so we kind of talked through this, but just to kind of clarify and remind you, weight and mass are not the same. Weight is a force. Okay, and I said that here, weight is a force. And, it's, the amount of object between the object and Earth. Usually, if you're on Earth, it could be the object and whatever planet you're on. And so it changes depending on the gravitational force. Mass, though, is just the amount of matter an object contains. And it's the same no matter where you are. Mass is the same whether you're on the Earth, if you're on Jupiter, if you're on, whatever. Mass and weight, of course, are related, though, because look at the weight equation, right? W equals mg. They're both in that equation. W and m are in that equation. So look, if this one goes up, this one goes up. If this one goes down, this one goes down. So just keep that in mind. Here's a kind of an interesting chart, and I put this in your notes too, so you could kind of look at it. Comparison of some just weights on Earth, because that's what this column is, this first column going down here. Some comparisons of some weights on Earth to like other planets. Like comparison, like if you weighed 75 on Earth, you would only weigh 12 on the moon, and 68 Venus, 28 Mars, 190 Jupiter, 87 Saturn. And that's because they all have different gravities. So this is because of the different gravities. So it's pretty cool. Now, kind of the interesting thing about all of this that we're studying is that what Isaac Newton did with finding gravity, and what I guess not what he did, but what other scientists did with the law of universal gravitation, is that starting in about the 1840s, the most distant planet that was ever known was Uranus. That was the farthest planet that they knew. And so they were studying it, and the rotation or the motion of it just did not make sense. They looked at it and they said there's just something not right about the way it was moving. And so they took that law of universal gravitation and they calculated it, and they said, the motion of it, the gravity of it just did not, like it just, and of course they couldn't see any farther than it. So, we're still talking 1840s, early time period. So the astronomers suggested that there must be some undiscovered planet that had to be affecting what was going on. And so by using the law of universal gravitation and Newton's laws of motion, two astronomers, it just so happened that two astronomers that were both working on this at the same time in two separate places, basically, they were working independently, calculated the orbit of this brand new planet. They basically, by using this basically Newton's theories, they were able to find in 1846, they were able to find the planet Neptune. So it's kind of cool how they took these physics things that had nothing to do with astronomy and able to apply it to, find this whole new planet, something that they couldn't see. They couldn't physically see it, but they knew it was out there. So you're going to use this information to start practicing some weight problems